Welcome back, everyone. Today we are going to be covering habitable zones. This is a fantastic suggestion from my buddy on X, Elg Comfort. Please forgive me if I'm mispronouncing that. But yeah, we're going to be discussing our own habitable zone, what it is. And well, first of all, I'd like to share a review with you real quick. I just got done seeing the movie The Presence, and it's getting really terrible reviews on Rotten Tomatoes because people are expecting it to be some kind of horror movie, and it's really not. It's more of a character study. You could say it's an art house movie, but it's a movie shot entirely from the perspective of a presence in this household. And yeah, they really marketed it poorly because people are expecting jump scares. And I'd just like to say, without giving too much away, it's a really, really good movie if you are looking for something different. So, like I said, the negative reviews come from basically, like I said, people, misleading advertising. I don't blame them because they did, as you can see, market it as something terrifying. It's not a scary movie. It's not even really a horror movie. Give it a shot. I highly, highly recommend it. It's got a nice ending to it. Don't let anybody spoil it for you. Okay, now in today's video, like I said, we're going to be going over habitable zones, what that means exactly. I zoomed out to Jupiter because Jupiter actually has some moons that, like Europa, that are believed to have liquid water. But a habitable zone stretches from just about Earth to Mars. It's this green section right here. What it means is this is the area, given a star's output, how much heat it's putting out, how much energy it's putting out, I should say, where water can be liquid on the surface. That's the key word. You can have liquid water underneath the ice on many of these outer worlds, and in fact we suspect there is, but if you're going to have liquid water on the surface where life can readily evolve, then you pretty much need to be in this habitable zone. Now you'll notice that Earth is on the inner part of it at 1 astronomical unit, or about 93 million miles, or I think 150 million kilometers, if my metrics right. And Mars is on the outer bit. Now obviously Mars is too cold for life, but that's largely because its atmosphere is so thin. As you can see, it's about 50%, a little more than 50% further away from the sun than the Earth. So, what does that mean? Well, if we're measuring in kilometers, and of course this is going crazy because it's our orbits are not perfectly circular, but it averages out to 150 million kilometers roughly, or 93 million miles. So that's 1 astronomical unit. So Earth is 1.01 technically, and Mars is a little more than 1.5. So, but that is the scope of, excuse me, that's the thickness, if you will, of our habitable zone. So what about other habitable zones around other stars? Our nearest neighbor is a triple star system, as many of you know. 2 stars very similar to our own sun, and then you've got Proxima Centauri, which orbits both of them. Now Proxima Centauri has 2 planets, Proxima b and Proxima c, that have been confirmed. You don't see C here because this is an older version of Universe SANDBOX, one I prefer using. But as you can see, Proxima b looks like it orbits in the inner regions of this habitable zone. Now, that's fantastic. Proxima Centauri is the absolute closest star to our own sun. So the fact that it has a roughly Earth-sized planet, on the inner regions of its habitable zone is quite amazing. Now, the problem, of course, is Proxima C orbits somewhere in that blue section. That blue obviously means it's too cold for liquid water on the surface. And they're showing the temperature to be 36 Celsius below. It's roughly the same in Fahrenheit. But look at the distance from the star. It is 4% as far away from its star as Earth is. So that puts it roughly just under 7 million kilometers. So I'm not sure what that is in miles off the top of my head, but it's definitely less than 7. So, you know, for frame of reference, I believe Mercury is about 45, 49, somewhere in there, million miles from the sun. So, roughly on average, because of course it has a very eccentric orbit, elliptical, you could say. Doesn't have anywhere near a circular orbit. But if we put Earth in this system, okay, see, we're just about at 1 astronomical unit. Okay, that's 146 million kilometers. I'm sorry, 14 million. 14 million kilometers. So the outer, I put Earth in the system so I could say that the thickness, if you will, of Proxima Centauri's habitable zone is only about 7 million kilometers. So this is because the star is so small. It's only 12% the mass of our sun, being a red dwarf. It's a tiny little star. It's 129 Jupiters, where, you know, our own sun is about 1,000 Jupiters worth of mass, of material, hydrogen and other elements, but mostly hydrogen. So yeah, it's a tiny little star. It's about as small as a star can be, honestly, because if you get below 80 times the mass of Jupiter, you're not a star, you're a brown dwarf. And that means that you cannot sustain fusion in your core. Brown dwarfs obviously are still hot, but they're nowhere near as hot as stars. Okay, so we're checking out Alpha Centauri B because Alpha Centauri A does not have any known confirmed planets. And I believe Alpha Centauri B's world here is hypothetical. I'm not sure if they've ruled it out completely, but when you are struggling with measurements on the verge of what instruments can give you, a lot of times there's some variance in the data, and those statistical anomalies, if you will, can lead scientists to believe that there's a planet. But of course, you know, we need long-term observation to see if we can confirm that data. Now, obviously, I'm checking. There's no atmosphere, which, you know, this is a flaw with the universe SANDBOX. I'm just trying to find the. There's a way to look at the planet with the temperatures. I don't think it's in here. It might be in the settings. But you can look at a planet not with visible light, but with based on temperature. Bear with me. I'm trying to find it here. But yeah, if you don't have an atmosphere, even in the habitable zone, you cannot retain heat. Okay, Mercury, being extremely close to the sun, still has a very, very cold, deadly cold night side. So, okay, this is if the habitable zone was a sphere. We got a couple cross sections of habitable zones here. That's interesting. That's much smoother, but it's still the same thing. It's a spherical habitable zone. We don't really need this though, because all the planets are orbiting within a plane. You know, a flat disk, if you will. I'm not seeing it. The reason why I was trying to find that, though, is so that you could see that, Alpha Centauri's world here, and same with Proxima. Their worlds are tidally locked to the sun. So one side is going to be always facing the sun. It's going to be extremely hot. Let me add Earth to this system. I'm trying to figure out how big these habitable zones are. Okay, so the inner part is right about at 1 astronomical unit. You can see that? And then the outer part is a little over 2. So you've got, this is a huge habitable zone. Remember, our habitable zone in the solar system is about half an astronomical unit. The reason why Alpha Centauri A's habitable zone is a full astronomical unit is because it's a slightly hotter star. So, yeah, see, this one's much smaller, 1.2 astronomical units and 0.6, so about 60% of an astronomical unit. That's much closer to the habitable zone in our own solar system. And Alpha Centauri B is about, I think, 10% less massive than our own sun. Okay, next we're looking at TRAPPIST. And TRAPPIST is a fascinating system because all of these worlds, all 1, 2, 3, 4, 5, 6, all 6 of them, and I believe there's a 7th confirmed now, all 6 of them are roughly Earth size. Some a little larger, some a little smaller, but this is a very small star. See, the mass is 93 Jupiter, so much smaller, and it wouldn't even be a star. This is roughly 9% the size of our sun. So that's crazy to think that you could get several stars out of the material in our sun. We may eventually do that billions of years from now. But yeah, our sun has something like 12 stars worth of material, so tiny stars, mind you, like TRAPPIST here. I'm looking at all these worlds, though. Some are wet and some are obviously so these are like ocean worlds. The designer got very lazy. That shouldn't be I mean, it could be an ocean world, but it should be frozen that far out. And that close in, this one's also an ocean world. That water would have all boiled away. See, it says the average temperature is 15 Celsius, which is normal, but it has no atmosphere. If you were to give this an atmosphere, it'd be something like Venus. It would be much, much hotter than 15 Celsius. So that's a important point to point out. The mass is about 30% Earth's, almost the same size, about 76% the diameter. But that is an important point to point out that this habitable zone requires an atmosphere. So that's one of the conditions. And it's a point that I make a lot in my terraforming videos, is we don't need a full bar of pressure to survive. We can get by with a lot less atmosphere, about 40% as much, and be just fine, especially if it's heavily oxygen. So, and that would make for a much cooler world if you don't have that much atmosphere to trap heat, all that extra atmosphere. You know, look at Venus. Venus has like 90 times Earth's atmosphere, and it's hellish because of it, because it's just trapping everything the sun puts out. Okay, so let's measure their habitable zone. It's somewhere in here. Good Lord, this is small. Like 2%, the distance to our sun. A little more than 2. All the way to 5%, 5.5%. So imagine a habitable zone, 2% of the distance from Earth to the sun that extends a little beyond 5%. That's way, way inside Mercury, and it's tiny. This planet, sorry, the star TRAPPIST is much more comparable to Jupiter than our sun. In fact, it's very similar in size to Jupiter, so absolutely minuscule compared to our star, the sun. So, all right, now let's have an extreme example. Where are you? I think there's currently a candidate that surpasses this star. Where are you? Come on. Oh, there it is. R136a1 is a star with about 260 times the mass of our sun. It is a monster star. Like I said, I think there's one that's been confirmed to be larger. But this thing is it's literally a monster. Its luminosity is 8 million times brighter than our sun. So that's beyond my comprehension. If we were to look at the sun without the atmosphere, it would literally cook our eyeballs. But this star has 8 million times the brightness. It's insane. It's crazy. So I'm not seeing a habitable zone. Some of these stars are such behemoths that it doesn't even bother with the habitable zone. And frankly, I did some experiments a couple years back where I just placed a whole bunch of Earths at different distances, and the distance that the Earth would be comfortable, to put it at a distance where the Earth is, what's going on here? Universe SANDBOX is tweaking. Give me just a second. So I'm trying to scroll back, but it's like I'm inside the star, but I'm not, so I'm going to start over. Yeah, you can get far enough away from the star that you're technically in a habitable zone, but the problem with it being 8 million times the luminosity of the sun is that's not just light, that's solar wind. So it is impossible. The solar wind is something like 1,000 times stronger even at that distance. So if you put a planet far enough away from the star that it's in a habitable zone, the solar wind is still going to strip the atmosphere off of it. There's no way for a planet to hold on to its atmosphere, unless it's something like Jupiter, a gas giant, or a brown dwarf with insane gravity. But anything the size of Earth or larger is just going to have its atmosphere completely stripped away. So we're going to have a little fun here. This is for the ones that actually stuck around. You get a nice little treat. We're going to destroy the Earth, and we're going to do it in very dramatic fashion. But just to show you what we're dealing with here, I'm going to put the Earth the same distance from the star as it is from our sun. There we go. 1 astronomical unit, perfectly. Okay, there's people on the night side, but not for long. All right. Okay, so see the temperature is going up. Now this is in real time. This is 1 second of the game for 1 second of reality. See, I've got it as close to 1 second as possible. So every second that ticks by for us is a second in the game. And the temperature, the average temperature, is skyrocketing. This is in real time. Keep this in mind, okay? On the upper right part of your screen, part of the world is already getting red hot. These circles here, this is material being stripped away. I told you the solar wind is insane. There's no way a planet this size can hold on to an atmosphere. Oh, that's beautiful. Australia is really getting the worst of it. Yeah, Australia is ground zero. So yeah, in the first fraction of a second, everybody would immediately be dead in Australia if you could magically teleport this world to another star, to this star in particular. And keep in mind, this is real time. This is seconds passing. You see the Earth is glowing. It's red hot on one side. Temperature is crossing 700 Celsius. just about half the planet is molten. But yeah, this is real time. Those of you who are very observant may have noticed that. Yeah, there's just material just being stripped away. Look at that. We're speeding it up. Now we're roughly at about 1.5 minutes per second. Under 2 minutes per second. So this is wild. Let's see if the Earth can last a full hour. Well, I was going to say, those of you who are more observant may have noticed that this is the second Earth I put down because I had to slow the clock down. The first one instantly vaporized because hours were passing. Now the night side is turning molten. Heat would directly be transferred through the planet to the night side. It would not matter. The planet doesn't even get a chance to rotate, to spin. We're literally still less than an hour after the Earth has been put into orbit around the star. I'm trying to see what this is in Fahrenheit. Yeah, you can see it's over 34,000 Fahrenheit in the hottest regions. The average temperature is, of course, much cooler. I say cooler with air quotes because it's not cooler at all, but you know, the Earth doesn't have much time left. It's rapidly shrinking. See that mass? And it's gone. So yeah, that's all she wrote. The Earth lasted less than 2 hours. The whole Earth was just vaporized and blown away in the wind. Insane. But yeah, this is you know, R136a1 is about the theoretical limit for how large a star, or at least a regular star, can be. There's variations of stars that may have existed early in the universe's life, but yeah. So I'd like to thank you all for watching the video all the way to the end. Don't forget to give me some suggestions. I love doing this stuff. That's our sun around this around this monster. It looks like a tiny moon. But oh, that's a joke. The sun's habitable zone is superimposed over this. As if, right? All right, thanks for watching. Take care.